Okay, everyone, once again, now we're going to continue to the part 2 of the films. There's 3 parts, 3 films, parts 1, 2, and 3. We already did part 1. Part 2, same rules, same situation. It is part 2 for electricity and magnetism, final exam review, parts 1, 2, and 3. All 72 problems fully solved on PDF document and available to students at the end of each film. 36 problems total we will do over these 3 films, folks, of the 72. They'll be solved on film, but the PDF for all 72 problems and their solutions will scroll at the end of each of the 3 films, parts 1, 2, and 3. So all 72 solutions for the entire practice exam, all 72 solutions, you will have scrolling in front of you at the end of each one of the parts of the review for the practice final exam, parts 1, 2, and 3. At the end of each part, you'll have the entirety of all the solutions scrolling for you. For numerous reasons, time considerations, and I wanted, it's not possible to get all 72 done on film, but if I get you 36 done like this, it's really very representative of what's going on with the 72. In addition to that, you do have, as we said, all 72 are going to be in front of you. So you can look at it that way as well. We can also discuss more in class for those of you that are in my classes. So this will pertain to part 2 that we're about to start right now. We've already done part 1, and now we will do part 2. Thank you. Hello, everyone. Let's talk about part 2 of the electricity and magnetism final review exam, and let's start doing some problems pertaining to that. Let's go to problem number 32 and see what it says here. 32, a radio wave signal which transmits at a frequency of 5.64 megahertz has what wavelength? C equals 3.00 times 10 to the 8 meters per second. Pretty basic, straightforward stuff. We should be getting these right very quickly, actually, when we're asked of this. We know that C equals lambda times F. They're asking here, has what wavelength? Well, to find the wavelength, you divide by the frequency on each side. You've got 3 times 10 to the 8th meters per second. 5.64 megahertz is 5.64. Mega is 10 to the 6. And that's the mathematics that has to be done to do it. It's as simple as that, folks. So you got it to here, you simply say, what's lambda going to be? When you divide, you go, there's a lot that goes on here. I mean, this right here is roughly 0.5. This is 10 to the second. This is about somewhere like 500, but a little bit more than that. When you actually do the mathematics to get this, well, let's back up a little bit. Let's back up for a second here. For some reason, I'm starting not to agree with some of this. No, actually, I am agreeing with it. This comes out to, again, you got the calculator, go for it. Let's see where we're getting here. Let's give the answer that they're giving. I mean, 3 divided by 5.64 is something a little more than 0.5. This division is 10 to the second. 0.5 something times 10 to the second is 0.5 something times 10 to the second is 50 something. Where you find that is C. We got 53.2 meters with the appropriate round-offs that they have. So that's what they're giving us. When we actually divide this out, we're probably getting a bigger number than that, or I don't know about bigger number, more decimal places when they're going there. But let's just, for the heck of it, let's just kind of do it. 5.31914. 5.31914 forgive me, 0.531954. So this right here is going to be, when you actually do the division, you get 0.5314815 right here, times 10 to the 2. That comes out to, when you grind it out, it's 53.19 roughly. You're getting this. What that's corresponding to is letter C. Regarding that, what's actually in our, and again, you'll see that when you look at the actual situation that's going on there. So you got that. So you're looking at this. Here's your answer. Same answer as that, essentially, and the round-offs are whatever they are, and you're getting these answers here. So let me get these erasers straightened out, folks. So we continue with the part 2, content. That's 32. Here's 33. For 33, let's see what we got here, guys. So we got 32. For 33, you play the game a number of ways here. It should be pretty straightforward when we're doing the problem. For number 33, light in air enters a diamond, n equals 2.42, at an angle of incidence of 30 degrees. What is the angle of refraction inside the diamond? So we're talking about a number of things that can be said. We can say, based on Snell's law, based on the equations we know, we can divide by sine theta 1 on each side. You can divide by sine theta 1 on each side, and divide by n2 on each side. So in that equation, you divide by sine theta 1 on each side, and you divide by n sub 2 on each side, and you work it. We don't know what the angle of refraction is. We'll call that this, sine theta sub 2. Theta sub 2 is going to be the angle of refraction. Well, I don't know what sine theta sub 2 is, because I don't know what sine theta sub 2 is, because I don't know theta sub 2. Sine theta 1, angle of incidence, is 30 degrees. So we're dealing with degrees here, not radians. Watch out how they're asking you a question. We are told that 2.42 is the index of refraction. That's N2. Okay? So 2.42, we don't know what theta 2 is, so we don't know sine theta 2. We do know this one is about 1, and this one is sine of 30 degrees. So let's see what we got here. That basically went like this, at least close enough approximation to what we need to do, and the rest is the mathematics that we need to solve. Sine theta 2 equals 1 over 2.42 times the sine of 30 degrees. The sine of 30 degrees, let's have a look here. The sine of 30 degrees is a half, so we got to here. We will get the inverse sine of sine theta sub 2 to get theta sub 2. We will get the inverse sine of this situation. Inverse sine of the sine of theta sub 2 is theta sub 2. inverse sine of this is something we have to work out. Luckily, we have the calculator. Let's see what we got. Inverse sine work this whole thing out. I got 11.9238, about 11.92. 11.92 degrees. It's going to come closer to the perpendicular line that passes directly perpendicular to the two interfaces. It's going to be closer to that perpendicular line from which they are measuring degrees. What does that tell you? Well, if it's a larger index of refraction, and 2.42 is a bigger, I guess say bigger index of refraction might be a better word. 2.42 is a bigger index of refraction than 1 is, so the angle, it'll tend to hug that line closer when we're doing something like that. So that's of interest when we do something like that. So when you look at, I got 11.9238. In my notes here, it's 11.924. Not a problem. We look at it, 11.924. I got 11.9 at A, so that's close enough. Again, you'll look at these, you'll know what's going on. Okay, looking pretty good. That's 32 and 33. We started at 32 for part 2. Let's go to 34. So we did 32 and 33. Let's go to 34. A ray of light travels from a glass to liquid interface. A ray of light travels from a glass to liquid interface at an angle of 23 degrees. That's the initial incidence. Indices of refraction for the glass and liquid are respectively 1.58 and 1.80. What is the angle of refraction for the ray moving through the liquid? So in other words, 1.58 for the glass, indices of refraction are 1.58 for the glass and 1.80 for the liquid. The initial incidence is at the glass, which is at the 1.58, and it leaves at the 1.80 for the liquid. The angle of incidence is 23 degrees right at the glass. What's going on? It's pretty straightforward stuff, once again, folks, when we're looking at this. So you see this. Okay, so same kind of argument, guys. Should be really straightforward when we do it. Snell's law, be on top of the game and get it right. It should be a very reasonable question. N1 sine theta 1 equals N2 sine theta 2. Sounds good, we know that. The initial situation consists of angle of indices of refraction. The indice of refraction initially, we're talking about the glass, 1.58. It hits at a 23 degree angle. And it's going into the liquid, 1.80 index of refraction, sine theta 2. Well, this equation is one equation, of course, and it's one equation and one unknown. It should be pretty straightforward. Sine theta 2 should be, let's divide by 1.80 on each side. Sounds good to me. Similar to what we did last time, guys. Just grind this out. Take 1.58 divided by 1.80, multiply it by the sine of 23 degrees. 1.58 divided by 1.80 times the sine of, I think they said 20. Did they say 23? Yeah, it was 23. .342975. Get the inverse sine on each side, like we did in the last problem, right over there, same argument. Get the inverse sine on each side, and you're getting the inverse sine set to degree, the modality of degrees, not radians. If they're dealing with radians, yeah, you're going to deal with radians, of course. 0.342975. If they're talking about radians, we're going to deal with radians, and we'll figure it out. If they're talking about degrees, and they're talking about degrees. What is the inverse sine of that? I got 20.058237, 20.06 degrees. They're probably just saying 20. No, they're doing this. 20.058, they're rounding it to 20.1 degrees. That is B. So this should correspond to B. 20.058. Let's see what else it went to. I'll probably truncate this at some level. 20.05828. Let's say I'll round it to that. I don't even think we need to go there. Well, their round off is 20. Their round off is 20.01. Okay, so and I think that was, let's see, was that the B value? That was B. Again, who cares what the letter is? I mean, know the right answer. We're just agreeing with their answer key. Be able to get the answer for any answer key to be able to get it right. Okay, that's what you're talking about. You started at 32. We got 32, 33, 34 for part 2. 32, 33, 34. Started at 32 for part 2, so we're doing pretty good. Let's go further. Let's go to 39 and see some of the stuff we could say there. Let me erase some of this stuff as well, guys. Let's see what we can say. All right, guys, for 39. An object is placed at a distance of 41.4 centimeters from a thin lens along the axis.
if a real image forms at a distance of 36.1 centimeters from the lens on the opposite side from the object, what is the focal length of the lens? Okay, pretty straightforward, pretty straightforward. You see different terminology in different places, in different books. So I'll perhaps write multiple terminologies here, I guess you could say. P is the object distance. Which is also equal to d sub object, which actually makes a little more sense if you ask me, but different books write different things. I've seen that written as well. Q, it depends on what book we're talking about right now as we're analyzing this stuff. I think there's even there's different letters that come into play as well in different books, more different than these. I'm giving like two sets of possible symbolism here, two sets of possible letter types to describe what's going on. Image, object distance, image distance. And I think there are other sets of letters that can be used as well to kind of get you there. Well, we got that. I'll tell you what, let's use P, but like I said, you could use either one. You could use this for object, this for image. To me, that's pretty straightforward. You also see it in books written like this. 1 over P . 1 over P plus 1 over Q equals 1 over F. What does that mean? We said the object distance, they're both on opposite sides of one another, and they're both positive if they're on opposite sides of one another. Remember that. We've talked about that. At least in the classes I've had when I've dealt with students, we've talked about that. So for right now, we're remembering that as well. Even though they're on opposite sides of one another, they both have positive values. They're on the same side as one another. One's going to be positive, one's going to be negative. Object's going to be positive, the image is going to be negative if it's that way. So let's see what goes on here, guys. You got this, and you got that. The rest is just mathematics, folks. There's a lot of ways to do this. I don't know that what I'm about to say is the easiest way to do it, but let's go for it. You could take 1 over this, get an answer. You could take 1 over this, get an answer. You could take 1 over that, get an answer. 1 over this, get an answer. 1 over that, get an answer. Add them together, and that's equal to 1 over F. Then get the reciprocal of both, and you got what F is. The reciprocal of 1 over F is F, and the reciprocal of all this is a mess if you haven't already written out what you need to write out. Let's just, for the sake of, I don't know, perhaps some rigorousness, to kind of look at the purity of the mathematics, for lack of a better way to say it, if that makes any sense. We're over here. When you grind all of that out, you're going to get the focal length to be 19.28. It's got to be centimeters because everybody was centimeters from the get-go. Okay? So it's doing what it's doing, guys. And the answer they have is A. That's 19.3 centimeters. What did I get? I got 19.28 centimeters. 19.28 centimeters rounds off to 19.3 centimeters. Good enough for me. That is 39. Let's go to 41. 41. A flat coil of wire consists of 20 turns, each with an area, each turn, and there's 20 turns, each with an area of 50 centimeters squared. Let's say that again. A flat coil of wire consists of 20 turns, each with an area of 50 square centimeters, is positioned perpendicularly to a uniform magnetic field that increases its magnitude at a constant rate from 2 Tesla to 6 Tesla in 2 seconds. If the coil has a total resistance of 0.4 ohms, what is the magnitude of the induced current that is occurring here? And they're talking about a lot of stuff going on here uniformly and at a constant rate and everything else. Okay, so we're looking at that. Let's take a look at how we want to actually say it. 41, huh? The induced current, again, the negative symbol there is for bookkeeping purposes. It's not of no significance. It's bookkeeping that is very significant. In other words, the induced current will move in a direction that will oppose the change in flux that was occurring. In plain English, write it down like that. So this is what's going to get us to where we want to go, or at least close to where we want to go. You can say a whole lot at this point, I guess you could say. I can maybe cut to the chase a little bit with this. We know that current, and it's a little different how I got it written in the actual notes here, but not too much different. Should not be very significant. Potential difference over the resistance will give you what I is. I will be equal to the potential difference, which is E, over R, which is equal to negative N, change in flux per unit time. That's all that divided by R. It's a little different than how I solved it. I went a little more piece by piece the other way. Doesn't matter. It's the same thing. It's coming down right to this. This is where it's all going to happen, guys. The money's right here. That's how it's going to go. So at that point, let's go. Let's see what we got. We've got, as they were telling us, they've got, I'm not going to worry about the negative. The negative we can kind of throw out of there. I can kind of just say, okay, since we're not worried, let me kind of put some absolute values here, guys. Okay, guys, looks not the great. I hate that when I. Okay, maybe see a little bit better there. So we got it to there. Let's see where this is going to go, man. We're looking at trying to get positive answers at the end of the day on this whole thing. We're talking about the number of turns. It's going to be the absolute value of all this. So it's going to be the absolute value of negative 20. Let's see here, guys. Got to get a little more chalk here. The absolute value of negative 20 times, well, it's changing, the B field is changing from 2 to 6. There are 50 square centimeters. 50 square centimeters are 50 times 10 to the negative 4 square meters. This is all happening in 2 seconds. Okay. We're going from 2 Tesla, from 2 Tesla to 6 Tesla in 6 seconds. There's 20 turns, each one with an area of 50 square centimeters. 50 square centimeters, 1 square centimeter is 1/10,000th of a square meter. 10 to the negative 4 square meters is 1 square centimeter. 10 to the negative 4 square meters, 10 to the negative 4 square meters is 1 square centimeters times 50 square centimeters. It's going from 2 Tesla to 6 Tesla. That's the flux for each one of the turns, and there's 20 of those turns. There's this. At the end of the day, you're dividing by, let us see, you're dividing by 0.4 ohms, or 4 times 10 to the negative 1 ohms. Well, I don't know. The way it's going to go essentially to where I was going before in the past. Let's just see where this thing's going. Let's try to make some sense out of it. It's going to absolute value is going to make this a positive number. 2 goes into 20 10 times. 10 times this difference is 4. 10 times 4 is 40. 40 times 50 is 2,000. It's 2,000 times 10 to the negative 4. I purposely wrote it in exponential notation, not 0.4, but 4 times 10 to the negative 1. 10 to the negative 1 goes into 10 to the negative 4. 10 to the negative 1 goes into 10 to the negative 4, 10 to the negative 3 times. 4 goes into here, 500. I equals 500 times 10 to the negative 3. I'm getting 0.5 amps. I'm going to check, though. I mean, if you got a little bit of time to check, always check what you're doing, guys, and see where this is going. We're making this claim. 0.5 amps. And where does that go? 0.5 amps, that's letter C. And that's letter C. Looking pretty good, you guys. Did 40 up through 41 so far. Not bad. Let's go to 43. All right, guys. For 43, somewhat of a longer, not necessarily. Let me just see here, guys. I'm looking at some other problem here. Some of these are more challenging than others. Here's 40. We did 41. Let's go to 43. And there it is. Should be pretty straightforward. 43, what is the equivalent capacitance? For number 43, what is the equivalent capacitance between points A and B? All capacitors are 5 microfarads. Figure it out. Starting at A. This one's C4, this one's C3, this one's C2. All capacitors are 5 microfarads. So C1 equals C2 equals C3 equals C4 equals 5 microfarads. So, let's see what we got here. We're trying to figure this out. The way we're going to figure it out is we're going to keep breaking this thing up. We're going to take these two capacitors that are in series and make it into a single capacitor, or equivalent single capacitor. The equivalent single capacitor and this other capacitor here that are in parallel, we're going to make them as though that we're going to get an equivalent capacitor right there, and that's going to be in series with this, and then we'll proceed from there. There's a lot of moving around, but it shouldn't be too bad. For a series situation, that's for series. For parallel, we got this. I'll tell you what I'm going to do. Let's find out what's going on up here, and then we'll just keep going. For this right here, we're going to say that because they're in series, I'll call it C sub A is going to be some equivalent thing here. 1 over C sub A is going to equal to the sum 1 over C sub 2 plus 1 over C sub 3. So for the top, the equivalent one is going to be C sub A. I don't know what that's going to be. It is equivalent to 1 over C sub A is equal to 1 over C sub 1 plus 1 over C sub 3. C sub 2, C sub 3. I'm sorry, guys. There's C sub 2, C sub 3. You got all this right here. Okay. Let's talk about it. I did it in different ways. What I'd like to do is probably make it a little easier. I did do it very much symbolically with non-numeric symbolism. Tell you what I'm going to do. I'm going to get off that. I'm just going to go here. This is a little different than how I showed in the notes here. The notes here are absolutely valid. But let's go 1 over 5 plus 1 over 5. Probably a lot easier to look at when you do it like this. That's 2/5. Get the reciprocal. It's 5 over 2. It's 2.5 microfarads. That's the equivalent of the top. If this whole thing on top is 2.5 and this on the bottom here is 5, this is 2.5, this is 2.5, this is 5, they're in parallel. The bottom thing is going to be, we'll call it C sub B, is the sum of, is basically the equivalent to this parallel situation. Up here we discovered 2.5 microfarads. This is 5 microfarads. 2.5 and 5 that are parallel to one another is 2.5 plus 5. That whole loop at the end of the day is 7.5 microfarads. That's all of this. And I've done it a little bit differently in the notes here. But that's 7.5. Here, at the end of all this, we did the whole song and dance here, guys. We got this thing right here. That whole thing is 7.5 microfarads. This right here is 5 microfarads. So let's go for it. Well, now it's a parallel situation. It's no longer a parallel situation. It is a series situation. If that's how you're going to do it, 1 over the very final equivalent situation. The very final equivalent, we'll call it C sub EQ. C sub EQ, 1 over C sub EQ is 1 over 2.5. It's a little different than how I showed it, but either way it works, what I've done. You got this right here. 1 over C EQ, multiply this by a special 1 called 2 over 2, you get 2 over 5, 1 over 5 here, 1 over C EQ, this is 3/5. Get the reciprocal. You get 1.67, 1.66 going on forever microfarads. See where that is. Okay, that, for some reason, we're not getting that answer. Either they did something wrong or I did something wrong, and all bets are I did something wrong, because the way I got it, let's see where I got it. No, I'm getting the answer they're getting. So if I'm getting the answer they're getting, I need to definitely get the answer that they're getting. So let's have another look at this, you guys. I'm sorry. Oh, forgive me. No, I think. Well, yeah. I mean, here's where I made the mistake. I hope this is where I made the mistake, or else I'm doing this completely all over. I do, if there's any redeeming aspect here, in the notes that you're going to have scrolled to you, as with everything, you have all the notes scrolled to you, the CEQ, the equivalent capacitance, is 3 microfarads. How are we doing this? Well, it'd be nice if I knew how to read my own writing. That'd probably help for starters. This is 2.5. Let us see exactly. No, there's a lot more to this than meets the eye, actually. I got everything I got. I should have stayed with my notes, right? Okay, the notes are completely right, guys. Let's just try this one more time. When we're doing this whole thing, we're trying to find what's going on here. This is C2 is 5 microfarads. C2 is 5 microfarads. C3 is 5 microfarads. It's in series, so it's 1 over 5 plus 1 over 5 is 2/5, and the equivalent, so 1 over CA equals 2 over 5. Get the reciprocal of both. CA is 2.5. 2.5 is up here. 2.5 is up here. 5 is right here. Because it's parallel, you just add them. You just add them because it's parallel. 2.5 plus 5 is 7.5. This is 7.5. This is 5. So 7.5, this is 7.5, that's 5. True, all of this is true. So at that point, let's try this again. 1 over the 5 starts on the far left over there, plus 1 over 7.5. Okay, that should work. If you multiply this one by a special one called 3 over 3, you get 3/15. You multiply this one by a special one called 2 over 2, you get 2/15. This is 1 over CEQ. 1 over CEQ, 3/15 and 2/15 is 5/15. Two things are equal if they're non-zero. If two things are equal and they're non-zero numbers, there are all non-zero numbers involved. If two things are equal with non-zero numbers, their reciprocals are equal. Okay, there it is, guys. Sorry about that. Watch what numbers you're putting in there. So that's the 43 we're talking about, guys. The answer is C, 3 microfarads. Not sure what I'm thinking. I'm not sure what I was thinking. I just simply took the 2.5. See, this one right here, when we added, when we talked about finding out the series combination here, where this is 5 microfarads, C2 is 5 microfarads, C3 is 5 microfarads, that combination right there was 2.5. microfarads. I'll be the first one agreeing with that. I mean, that's what that was. You did that. And you got 2 microfarads. And this thing is 5 microfarads, initially at least. It's what it was. It's 5 microfarads. So if you take the 5 and the 2.5, the 5 and the 2.5, add them together, you got this. And this is what I should have used. This one, no manipulation took place, and that's the one you're going to use. I should have used the 5 microfarads and the 7.5 microfarads, the 5 microfarads and the 7.5 microfarads, which I finally did correctly and got all this. And that gets you to here. Okay. Sorry about that, guys. But there it is. All is well that ends well. My notes are a little more symbolic in nature when I take care of it, and apparently they work pretty good because the answer is flat out okay in the notes. And now you see another way you can maybe look at it. There's your final answer. 3 microfarads for the equivalent for number 43. All right, let's do 48, 49, 50, and see where we are. All right, guys. Let's look at 48. Problem number 48. In an AC series circuit, the capacitive reactance is 219 ohms and frequency is 56 hertz. What is the capacitance? They're telling us the capacitive reactance is a particular amount, and they're giving us the capacitive reactance in a series circuit. And so we're trying to figure out what the heck is going on. For number 48, in an AC series circuit, the capacitive reactance is 217 ohms and frequency is 56 hertz. What is the capacitance? It should be relatively straightforward to look at something like that. For number 48, they're telling us the capacitive reactance is 1 over omega times C. That's what it is. That implies that if you solve for C, multiply by big C on each side, and divide by x sub C on each side, we've got that situation. True. Omega is 2 pi f, and x sub C is x sub C. So this is an important, I guess, conclusion to have in mind. Okay, yeah, it's pretty. That's about it. I mean, at that point, guys, C is going to be 1 over the product 2 times pi times 56 times 217. And that's it. I mean, you grind out, you get all the stuff in the bottom here, you multiply all this bottom stuff out, get an answer, get its reciprocal, which is 1 over all that stuff. In other words, 1 divided by that product should give you 1.31 times 10 to the negative 5 farads. Is there another way to write that? Yeah, make it bigger by a factor of 10 and make this smaller by a factor of 10. You know why I'm doing that. We've seen micro enough times. Now, I don't know if they're actually going there. They might not even have it there. They may have it in exponential notation. What they're having here let's see. I mean, let's see what they said. They might have just stayed here. Either way is fine, guys. There's a lot. Any one of these. Any one of these is fine. Haven't really looked at the answers just yet, or at least the answers the way they're reporting them. But they got 1.31 e to the negative 5. That means 1.31 10 to the negative 5. That's right here. Which one is that? That's C. And that's C. All right. Let's look at 49. 49 is saying, what is the phase angle of an AC series circuit that is constructed of a 14.5 ohm resistor along with a 16.5 ohm inductive reactance and a 9.41. These are all ohms now, right, guys? What is the phase angle of an AC series circuit that is constructed of a 14.5 ohm resistor along with a 16.5 ohm inductive reactance and a 9.41 ohm capacitive reactance? Okay. Basically, you want to watch out. You want to follow the way we were taught how to do it and what is what. In terms of the tan of phi, where phi is going to be the phase angle, there's some fascinating mathematics that goes into discussing this in its own right. You got x sub L minus x sub C over R. Well, what does that mean? Well, it means what we know. It means what we already know, guys. I mean, at that point, the tan of phi is going to be associated with, they basically told us x sub L is 16.5 ohms. Everything's ohms here, guys. X sub L is 16.5 ohms. X sub L is 16.5 ohms. X sub C is 9.41 ohms. So X sub L 16.5 ohms. X sub C 9.41 ohms. We know that the resistance is 14.5 ohms, and the rest is just relatively basic mathematics that we're going to knock out and get it right. So you're looking at this. That's 0.48896555172. I just don't think I took that to enough decimal places. What do you guys think? Don't have to, guys, really. The big thing is get the inverse tangent on each side. The inverse tangent of the tangent is phi. The inverse tangent of this is inverse tangent of this mess. Again, I don't know how, basically play it on the safe side. I mean, I know I'm making jokes about it, but it's not a bad idea to take this thing really, really far out, especially when there's like multiple operations taking place on the whole thing. So basically what you're doing is, you're getting, the tan of phi. So when they say to you, for this right here, you get this for an answer, you're basically getting, on each, if you do the same thing on each side, you still have an equation. Get the inverse tangent of the tangent function. Get the inverse tangent of this mess. The inverse tangent of the tangent function is phi. The inverse tangent of this is this. We're dealing with degrees, not radians, right? We're getting 26.06 degrees. They probably got 26.1 degrees, maybe just 26 degrees. Probably 26.1 degrees. 49 has 26.1 degrees as the answer. That is letter A. A is 26.1 degrees. So that's letter A, you guys. Not too bad. So we got 48, we got 49. Let's go to 50. Let's see what they're saying here. This one, somewhat, a little bit, no, that's not too bad actually as well. Now, none of these are really that bad, you guys. You don't want to make any careless mistakes. You saw the careless mistake that I made earlier, and we had to go back and kind of look at it, but that's all right. We caught it. Took us an extra 2-3 minutes, but we got it. We got it right. Watch what you're doing. Any one of us can make the mistakes, you guys. We try not to, and we always double check it, and we find where we are. And then we correct it to the best of our ability. So you're doing great, guys. Let's get through this. Let's do well. For problem number 50, let me guys, as usual, I'm running out of chalk. So we'll see. I mean, I said for the earlier thing I got there, guys, you may not even see much of it. I might have it edited out a little bit, how we actually did 43. I don't want to see you have too much of an issue that I had there. But the moral to the story is you can write in the wrong stuff and have the thing go not so well. So for 43, we'll kind of look at that. But like I said, on mine, I'll take care of it. You're looking at it. It's completely right. At the end of the day, it's going to be completely right. I'm not going to hand out anything to you that's not completely right. To the very best of my ability, that's definitely going to be the case. Everything's going to try to be everything's going to be done as well as can be done. So hopefully that's going to be all right for all of us. So that's it. So look at number 50, you guys. Number 50, an AC series circuit contains a resistor, 30 ohms, a capacitor, 1.2. Now this is a series circuit. It's an AC series circuit. It contains a resistor of 30 ohms, a capacitor of 1.22 microfarads, and an inductor of 154 millihenries. So it's, we have, an AC series circuit. It's containing a resistor, a capacitor, and an inductor. The resistor is 30.0 ohms. The capacitor is 1.22 microfarads, and the inductor is 154 millihenries. What frequency should be used to create a resonance condition in the circuit? Okay. We can do it. I may have to erase a little bit, guys. We'll see what we can do. We are looking at a number of ways we can do this, I guess you could say. Let me not get too adventurous with it, I guess. You've got, let me see here, guys. Give me 1 second here. Just see where we're at. R equals 30 ohms. Okay, so R equals 30 ohms. XC, just for the record, we won't put an actual number here, though we can find the number, certainly. R is 30 ohms. X sub C is 1 over omega C. X sub L is omega L. Okay, so those play a pretty big role here. We got this, and this right here. We've got this. So
All right, guys, let me try to erase a couple here. Okay. Well, okay, we've got the information that we have. For there to be a resonance situation, let's not forget, you got to have XC equal to XL. You got to have 1 over omega C equal omega times L. Multiply by omega on each side, multiply by omega on each side, and get omega squared. Well, let's do a couple things. Let's multiply by omega on each side and divide by L on each side. And you got this. Square root each side. So the criteria, the whole situation is not as intimidating in reality as we might think it is. You're basically you're saying this is where it's got to be. That means this. Solve for omega squared, multiply by omega on each side, and divide by L on each side. You got this. Square root each side of this last equation down here, and you get this. You know that omega, they want the frequency. Well, the frequency is f. 2 pi f is omega. And you got this. Not too bad. Stuff we've seen. Stuff we have seen, guys. This should be pretty basic. Divide by 2 pi on each side, or multiply by 1 over 2 pi on each side. It's about where they're going. It's about where they're going. It's about as tough as it gets. I mean, at this point, you're just really careful not to do anything careless. 1 over the product, 2 pi, whatever that's going to be. 1 over the product, 2 pi, whatever that's going to be. And 1 over the square root of all this. Well, they told us that L is 154 millihenries. That's 154 times 10 to the negative 3. They told us that so that was the inductor. The inductance is 154 times 10 to the negative 3 henries. The capacitance is 1.22 microfarads, which is 1.22 times 10 to the negative 6. Well, I mean, it's a little bit of a mess, but certainly reasonable. 154 times 1.22 is about 180 something. Maybe 2, I mean, let's do some ballpark figures here, guys, if you want to do this. 154 times 1.22, and we can kind of do some of this in our heads when we're doing it, I guess you could say. 154, all this on the bottom now, 154 times 1.22 comes out to about 190, somewhere like that. Ballpark 180, 190. 10 to the negative 3 times 10 to the negative 6 is 10 to the negative 9. Let's say 190. 190 times 10 to the negative 9 is the same as 19 times 10 to the negative 10. Square root of 19 is, I don't know, let's say ballpark of 4.5. Square root of 10 to the negative 10 is 10 to the negative 5. 4.5 times 10 to the negative 5. 10 to the negative 5 goes into here 10 to the 5 times. That is 100,000. 100,000 and put 4.5 into it. Interesting point in its own right, isn't it? So it's going to be 100,000 times 4.5 is going to be somewhere. Let me try to think, guys. And you're multiplying by 1 over 2 pi. I tell you what, there's an awful lot of stuff, guys. It really is. Some ballpark ideas, like I said. We don't really need to go like the way we're going. Okay, we entered the dance. Let's go for it, I guess you could say. I'm thinking at the end of the day, you're getting, okay, I actually did a lot of things wrong here, guys. 154 times 1.22, let's put that answer somewhere in the ballpark, you guys. Let's put it somewhere in the ballpark of about 190. 190, this is 10 to the negative 9. 190 times 10 to the negative 9 is the same as 19 times 10 to the negative 8. 19 times 10 to the negative 8. The square root of 19 is about 4.5. The square root of 10 to the negative 8 is 10 to the negative 4. So that was a mistake I made. 10 to the negative 4 comes up here. That's 10 to the 4. That is, 10 to the 4 is 10,000. 10,000 divided by 4.5 is about 2,200, something like that. Divided by 6 something comes out to about 300 something, between 300 and 400. Okay. Yeah, that's my instinct. Let's see if the mathematics grinds out to about between 300 and 400. They're getting an answer here of 367.18 hertz. Okay, guys, so yeah, again, I did a little bit of a song and dance there for a few minutes that we didn't need to do, but it is a kind of neat situation. You multiply the 154 with the 1.22, you get about 190. 10 to the negative 3, 10 to the negative 6 multiplied together is 10 to the negative 9. 190 times 10 to the negative 9 is the same as 190 times 10 to the negative 9 is the same as 19 times 10 to the negative 8. The square root of the product, 19, the square root of the product, the entire product, 19 times 10 to the negative 8, is about 4.5 times 10 to the negative 4. 10 to the negative 4 divides into here, it becomes 10 to the 4. It's 10,000 divided by 4.5, about 2,200. This is between 6 and 7. Between 6 and 7, let's say 7, whatever. Let's say 6 something. 6 goes into 2,200 about between 300 and 400 times. Yeah, our gut was all right. If you run into trouble and you want to check what you've done, did I plug in the right numbers? Am I getting a ballpark answer at the end of this? It's a bit of a trek. Am I getting between 300 and 400? Somewhere around there. Yeah, I sure am. When we're doing this, you look at it, and we're saying, okay, that was number 50, you guys, of course. And we're getting this. Let me see what we're getting for an answer, what they're actually saying. And they're writing a little differently. I wrote 367.18 hertz. They're writing 3.67 times 10 to the 2. 3.67 times 10 to the 2, they got it. That's D. 3.67 E plus 2 hertz. They're writing 3.67 E2. You might have put a plus in there too. Let's see how they actually write this. 3.7 E plus 2 hertz. That's just, you're going to see some different terminology and uses of symbolism. Please be aware of it. It's the same thing. So we got that. It just means essentially the same thing as what's going on here. And what they were saying for an answer there, I think that's C or D. That's letter D.
That's letter D for number 50. From all of this. So either one of these, again, be aware that's some of what you see in some of the learning management systems. They may write the exponents in this sort of a manner, or something close to that, or some other ways. So just be aware of the language that's out there and try to have some decent control of what's going on here, guys. So what we have here is 48, we did 49, and I erased it, and all of this here was 50, culminating right here for problem number 50. Let's do 51 and 52 and see where we are. Okay, folks, let's keep going. For 51, I got some pretty interesting things here. Let me just see exactly where we're going to go here. I got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. All right, guys, let me see about where I can go here, guys. Let me just take this as far as I can. For number 51, a radar pulse sent out to an airplane at a distance of 24.9 kilometers will return as an echo to the source in what time interval? Okay, pretty straightforward, pretty basic. Let's get it right. We know that distance equals magnitude of velocity times time if everything's going straight. So if everything's going like in a straight out direction, stuff like that, the acceleration is not happening. There's no acceleration happening. It's going straight out distance, and there's just no acceleration for our purposes. Distance equals speed times time. Time is equal to distance divided by v. The distance is, to get there is 24.9 kilometers, and then to come back is 24.9 kilometers. So 2 times 24.9 kilometers, it's got to go there and come back. The speed v, in this case, the speed is going to be the speed of light, which is 3 times 10 to the 8 meters per second. It's 3 times 10 to the 8 meters per second, or it is 300,000 kilometers per second. Because if you put 1,000 onto this, you get 3 times 10 to the 8th. So this thing right here is 3 times 10 to the 5th kilometers per second. It's up to you what you want to do. I go 3 times 10 to the 5th kilometers per second. The kilometers are going to cancel. That's going to flip up. The whole bunch of stuff is going to happen here, guys. This is 49.8. This is 49.8. This is 3 times 10 to the 5th. A lot of ways you can do this. A good estimate is this. This is about 50. This is 50. This is 300,000. 50 goes into 300,000 6 times. 6 times 10 to the 5th. It is, forgive me if I can do it one more time here. If this is about 50 and this is 300,000, 50 goes into 300 6 times, you got 6,000. 1 over 6,000 seconds, roughly. 1 over 6,000 seconds is the time. That is about
0.17 times 10 to the negative 3 seconds. 1.7 times 10 to the negative 4 seconds. Something like that. We can get a ballpark idea of what's going on sometimes, guys, and kind of just get ourselves through where we got to go. Well, they got 1.66. It should be 1.67. It's probably a better estimate, but I got t equals 1.66 times 10 to the negative 4. Didn't we just say that? 1.67, it's really 1.66 going on forever, times 10 to the negative 4 seconds. We said essentially that just now. Here's your answer. Where are we now? Well, that's your answer. As simple as that. I said 1.67 roughly. The answer is the answer that they write is something on this order. We're not going to nickel and dime that, guys. It's not going to be too far off from either one of these. The way that frequently is going to get written is 1.66. Forgive me. The way that's going to get written is 1.66 e negative 4, like that. Let me see how they wrote that. Correct. The answer is C, 1.66 e negative 4 C. They're pretty close to each other when they write that, but 1.66 e negative 4 seconds. Sounds good to me. All these are basically in the ballpark of where you want to be. No, you're not going to get something radically off of where the answer should be if you're doing the mathematics correctly. Again, some of this stuff, if you get into trouble in terms of time, you can do a lot of this stuff in your head too. I don't know if it's faster or slower. It's a good estimate though. I mean, this is about 50. This is exactly 300,000. At least we write it down as 300,000. 50 goes into 300 6 times, so it's 6,000 on the bottom. 1 over 6,000 is 0.16666 going on forever, times 10 to the negative 3. 0.166 times 10 to the negative 3 is 1.66 times 10 to the negative 4. And that's the whole argument here, guys, when they're doing that. So we got that. All right, guys, for number 52, for problem number 52, an observer is moving in space toward a distant star at 50 kilometers per second, while the star is moving toward the observer at 180 kilometers per second. He's moving toward it. The person, whoever they may be, is moving toward it, and the object is moving toward them. So an observer is moving in space toward a distant star at 50 kilometers per second, while the star is moving toward the observer at 180 kilometers per second. The relative velocity is 50 plus 180 is 230 kilometers per second of approach. The 50 plus 180 is 230 kilometers per second of approach, is what I'm telling you. And they're telling us as well. That is the relative velocity of approach, 230 kilometers per second. What relative change in frequency of the light from the star? What relative change in frequency of the light from the star as seen by the observer? So, yeah, it's pretty straightforward that way. It is by approach. And again, I have this in much more detail elsewhere, but we're saying the observed frequency of light is roughly the source plus or minus, and this is the relative of approach here. If there's an approach, it's plus. If they're going away from each other, it's minus. Going away from each other is minus. Approaching each other is plus. So it's plus. And that's if U is much smaller than C. And we have all those criteria. So we have this
we have Fs 1 plus u over c. A lot of ways we can do this. They're asking a number of things here, and we'll answer them. I guess the way we want to answer them is, yeah, there's some pretty interesting things here. Okay, let's talk about this, because I don't want to. I want to stay more with overt symbolism on this, meaning, at least what I'm trying to say here is, more with non-explicit numeric symbolism when I'm doing this. They want to know the change, okay? They want to know, what relative change in frequency of the light from the star is seen by the observer. Well, let's see what the observer sees. I mean, we're looking at delta F. Delta F is going to equal F0 minus Fs. F0, we just said, was this, more or less, pretty close to it. So F0, we said, was this. F0, we said, was this. It's Fs 1 plus u over c minus Fs. Okay, that's pretty important. There's a lot we can say here. That's the delta F, folks, and that's equal to this. And all this is of interest. This Fs, if you distribute it here and distribute it here, you get Fs plus, you get basically Fs plus Fs u over c minus Fs. Well, that and that cancel. They cancel, guys, and you got this. This is at the end of the day what the delta F is going to be. Now we said, I mean, if u is positive, if u is a positive number, well, we regard u as positive if they're going toward each other. So you can always leave it as plus right here. If you go plus or minus. There's so many ways to write this, guys, actually. In this regard, I guess you're going to call everybody positive, and you're going to do plus a positive if they're going toward each other, and minus a positive if they're going away from each other. Or you could just write it generically as positive, and the u could be a negative or a positive. U is negative if they're going away from each other. U is positive if they're going toward each other, if you call this the generic positive, the generic plus sign. You can just have a generic plus sign. And the u is negative if they're going away. U is positive if they're going toward each other. Simple as that. If you're going to go plus or minus, everybody's positive. If it's going away, it's a positive number, but you're using a minus. If they're separating from each other, you're using a minus. If they're going toward each other, you're using a plus. But the u is plus in each case. It's just going to be minus a plus if they're going away from each other, plus a plus if they're going toward each other. Well, they are going toward each other, so we know that. What we have here is they're going toward each other, so it's going to be a positive answer. We are told a number of things. So let's see, they're saying, okay, we could say even more, actually, is what we can do. If we're here, they want to know the percentage that it's off. Okay, well, let's do that. As opposed to the original source. So they're saying here, guys, you're going to divide by Fs on each side to actually get that right. What is the relative change in frequency? The relative change is a ratio. It's a ratio that you're going to do right here. So basically you divide by Fs on each side, and delta F, you're going to divide by Fs on each side. Delta F over Fs. Right, correct. Delta F, divide by Fs on each side, so it's delta F over Fs equals U over C. That's it. That's symbolically the answer without putting in the actual numbers. Let's put in the numbers. It's 230 kilometers per second. Let me use what I already know about the speed of light. It's 300,000 kilometers per second. I could have converted everything to meters per second, but if I already know, and if I'm comfortable with what C is in kilometers per second, and I'm comfortable with what U is, we're okay. You get to here, and at the end of the day, all of this, let me just not write it again, guys. It's right here for us. At the end of the day, what does that come out to? It comes out to well, this comes out to a lot of stuff here. Let's see what it does here. I got 7.666 times 10 to the negative 4. 7.666, I'll put a 7 here, times 10 to the negative 4. That's equal to 7.6667 times 10 to the negative 2%. So, let's kind of put this up higher, guys. There's a lot of ways you can write this. I mean, the basic thing is, I think it gets rounded off. All of this can round off to about 7.7. 7.7 times 10 to the negative 2. Right. 7.7 times 10 to the negative 2% is 0.0. I mean, it's not a big deal. The big thing is, guys, this right here actually, technically, this is valid. This is certainly valid. This is also okay. I guess you got to look at how they want you to give the answer to the question. You can run that out a little bit and get 0.07666, which is just 0.07666 going on forever. That's 0.077%. Maybe that's easier to look at the way they wrote it. So that's a neat problem in its own right, guys. Let's see where they got that. And that's an increase, right? And the answer to that is A, 0.077% increase. .077% increase. We got that. Again, guys, this can be done really, when you're doing this on your own, you're not running across, you're not running across a classroom trying to erase stuff, trying to write stuff. You're kind of doing it on your own. You can do a lot of it in your head. You can do a lot of it pencil and paper, and you don't have to explain any of this stuff. The only person to whom you explain this is to yourself. Get the right answer and move on. So it should go pretty smoothly for you when you do that. The answers are pretty comprehensive that I give. The workout here is okay. It's the same as what I'm showing here. That is number 52. Let's do 54 and we'll leave it, and I'll leave the rest for part number 3. Let's try to let's do number 54 though. Kind of take that if we can. Okay, guys. Let me, like I said, I'll probably do 54. I might even be able to do 55 and then kind of leave the rest for us to finish it out for the very last situation that we're going to be doing. Let us see. For problem number 54, resistors of values R1 equals 6 ohms, R2 equals 4 ohms, R3 equals 10 ohms, and R4 equals 7 ohms are combined as shown. What is the equivalent resistance for this combination? So that's 54. Let's take a look at it. Okay, guys, so for 54, they're doing a lot of stuff here. We can do it with some very interesting symbolism, not using explicit numbers. Perhaps it's easier with the explicit numbers. I tend to go more with the non-numeric, non-explicit numeric symbolism sometimes. I don't always know that that's a good idea. Maybe it's not the most efficient way to do it when you're taking a test. We know that if things are in series, you're going to add like this. We know that things in parallel are in parallel, we got something like this. For how things add up, how things are calculated, etc., etc. We've got this. Okay, two things to look at. I don't know. I mean, there's a part of me. I don't know. There's easy ways and hard ways to look at this. I mean, the way I would kind of, I guess, go about it. Maybe let me, like I say, I got the notes here, guys. Make sure we're in agreement. Right. I tell you what I'm going to do. I've got the notes here. It'll come out just fine if you follow my notes. Let me go a little bit off, away from the notes, or slightly off the notes, not too much. R1 is 6, R2 4, R3 10. So 6, 4, 10. And R4 is 7. Let me just see if there's, maybe if you're looking at this and you're in a hurry, obviously you're trying to do an exam. You should be in a hurry, right? Got this. You got this. Running out of chalk, guys. All right, we got this. This is the initial setup that they're giving us, right? How do you want to do it? Tell you what, I mean, I could take these two, probably the easiest way to, I think the easiest way. Again, I don't want to say I gave a very elaborate and sophisticated approach to the problem. It was a few steps and it came out just fine. You can do it the way I do it in my notes. Essentially, it's the exact same thing I'm about to do here, but I'm using the explicit numbers pretty much up front quite a bit. So you can kind of look at it and say, okay, well, as we do this, I'm going to take these two, since they're in series, and make it 14 ohms altogether. That's right up here. That's these two together, gives you 14 ohms. This guy down here remains 7 ohms because he's by himself. Let's look at this parallel arrangement and get an answer. Well, you got 7, you got 14. Let's get an equivalent partial, equivalent right side loop. Let's get an equivalent resistance right side loop is going to be 1 over 7 plus 1 over 14. Multiply this by a special one called 2 over 2, get 2 over 14 plus 1 over 14. This is not the only way to do it. Some people just get a decimal here. They divide this out, get a decimal, divide this out, get a decimal, add them, and then get the reciprocal of that sum. That's fine too. That's fine too. This is 3/14. Get the reciprocal of each side. You get 14 over 3. That's going to be 4 2/3. Let me leave it like that for now. I know it's 4.67, 4.6 repeating. I get all that. Let me leave it like that for right now. This whole song and dance on the right-hand side, this big loop right here, this whole song and dance is 4.67 ohms, roughly. 4 2/3 ohms. Now they're in series, add them together, and the equivalent is all of it. Our equivalent is going to be the 6 ohms plus the 4 2/3 ohms. Our equivalent, the whole thing, is going to be 10 2/3, about 10.67. About 10.67, 10 2/3, 10.67 ohms. That's about 10.7 ohms. Let's see where they gave. Now, again, I more or less did that earlier, you guys. More or less done earlier. I mean, so there it is. Let's see where that is. Yeah, they got letter C, which corresponds to 10.7 ohms. Letter C is 10.7 ohms. So that's for 54, you guys. That's 54. Let's try 55, and then we'll leave the rest for test 3. For part 3 of the review test, part 3. So you got what you got. '55, problem number 55. 3 4-ohm resistors are connected in parallel to a 14, forgive me, let me start that again, please. For number 55, 3 4-ohm resistors are connected in parallel to a 10.4 volt battery. What is the current in any one of these resistors? The current is equal. If things are in parallel, actually, that's not true. That's not true. Necessarily true. When it's parallel, the voltage is the same. The potential difference is the same, not necessarily the current. Now, we are talking about a situation when there are, I mean, all that is given to us, and we're assuming that all that is given to us is all that is going on, nothing more than that. All that is given to us is all that is going on, and nothing more than that to our knowledge. So we think that's it. I mean, three 4-ohm resistors are connected in parallel to a 10.4 volt battery. What is the current in any one of these resistors? Okay. There are a lot of ways to do it. Let's find the total current, and it should be pretty straightforward, guys, at that point. So for 55, if you're talking about things being in parallel, and each resistor is identical to each of the other two resistors in terms of the resistance, all three have the same amount of resistance. 1 over R, we'll call R is the 4 ohms we're talking about. But, 4 ohm resistors, R is 4 ohms in each one of these. Well, let's not worry about that just yet. Let's just do this. 1 over R plus 1 over R plus 1 over R is 3 over R. If you get the reciprocal of both sides, you know what we're doing here, guys. We're doing it again. If two items are equal and they're non-zero numbers, their reciprocals are equal and defined. These two are equal to one another. Their reciprocals are equal, under the conditions I've already described. So these two are equal, get their reciprocals. The reciprocals are going to be equal. You got this. This guy right here, well, what is that? I mean, that's an important thing. Didn't we say that R was equal to 4? Now we got to actually put it in there and figure out what's going on. If R is 4, we got 4/3. We got 4/3 ohms. That is equal to the equivalent resistance. The amount of current entering and leaving is equal to the potential difference divided by the equivalent resistance. It is 10.4 divided by 4/3, which is 1.333 going on forever. Let me just write it as 4/3. Here's 4/3, here's 10.4. Looks pretty good to me. At the end of the day, you do this. I mean, 4 goes into 10.4 2.6 times. The 3 flips. 4 goes into 10.4 2.6 times. The 3 flips. So 3 times 2.6 is 7.8. The amount of current, start to finish, the equivalent current going through there, is 7.8 amps. Well, they didn't ask us that. They didn't ask us the equivalent of what goes in to those loop. What goes in before they start looping? What goes in is this amount. What comes out is this amount. Yeah, we know that. Okay, we know that. Now, that's what's coming in. Now, here it is. The total current I is 7.8. Total current is equal to I is equal to 7.8 amps. 1/3 current in each one of the resistors. So basically, each one, I mean, the I is equal to I sub 1 plus I sub 2 plus I sub 3. Yeah, here's the thing though. There's the same potential difference in each branch, and there's the same resistance in each branch. So the V, there's a potential difference delta V1 here, there's a potential difference delta V2 here, there's a potential difference delta V3 here, but delta V1 equals delta V2 equals delta V3. It's the same potential difference, and potential difference divided by resistance, potential difference divided by resistance is the amount of current. They are equal currents in each one of these. I1, I2, I3 are all equal. This is the total. I don't know where to go, guys. I'm running out of room is what I'm doing.
you guys understood where this problem was going maybe 5 minutes ago, but and you don't have to do this. You're not delivering a lecture when you're doing these exams. Just know what you're doing. You don't have to run all over the place. You just have to make it make sense to yourself. I total, the I total, you guys, is I1 plus I2 plus I3. The I total is 7.8 amps. Each one of these is some kind of I. I've been using I over there. I should have maybe used another I. Better one to put here. The I total going in, I could maybe put, total, for lack of a better word right now. That's fine. I1, I2, I3 are all equal. Why are they equal? I1 is delta V1 over R1. I2 is delta V2 over R2. I3 is delta V3 over R3. R3, R2, I hope I said that right. I1 is delta V1 over R1. I2 is delta V2 over R2. I3 is delta V3 over R3. R1, R2, and R3 are all equal to 4 ohms. Each one is equal to 4 ohms. The potential difference across each one of the branches are also equal because they're in parallel. Delta V1, delta V2, delta V3 are all equal. Each one is equal to delta V, let's say. Let's just call it delta V for our purposes right now. Delta V1, delta V2, and delta V3 are all equal to each other. We'll call it delta V. R1, R2, and R3 are all equal to each other. You got this. So what happens here is, guys, as you look at this, what was that potential? That's kind of an interesting point in its own right. I mean, that's what they're all equal to. Each one's got 10.4 volts. Each one's got 4 right here. And, that makes sense. When you do this, you're going to get 2.6 amps. Each one is going to have 2.6 amps associated with it. At the end of the day, guys, that's what's coming. I mean, each one of these are equal. We'll just call them I. Divide by 3 on each side, you get the 2.6 amps that we're talking about. Same argument all the way around, you guys. All right. So where is that located? So 2.6. Yeah, there it is. There it is. Gee, I thought I'd gone down the wrong path here again. It can happen. It can happen to anyone, right? C is 2.6. So you got C. Okay, a couple looks at it to get it there, guys. That got us through 55. We will finish this discussion for the review for electricity and magnetism final exam. We will finish this verbal discussion, film discussion. We will finish it with part 3 that's going to be completed shortly. And that'll be it. It'll be 36 problems total that you'll have been shown kind of firsthand, almost in person, not really on film, sort of pretending that there are people here with me, and trying to get this done. So you see them on film, 36 of those problems. All 72 problems are fully solved for you, and they are all scrolling at the end of each one of the films. Part 1, Part 2, and Part 3. At the end of each one of those, Part 1, Part 2, and Part 3, all 72 problems from the exam are written for you. You see them, they're scrolling, and all the solutions looking like this are going to be scrolling for you. Okay. Thanks for your time. We will be done shortly. We'll see you very soon. Take care. Bye now.